Yeah, I kind of doubt that, honestly. But anyway, I will begin with a word of prayer. Dear Father, we thank you for this day. Again, I thank you for this class and these students to help us to glorify you what we do this day, Lord. In your name I pray, Lord Jesus. Amen. So we are finally reached the end point of differential calculus of one complex variable. At least everything I've got to tell you guys about it. Is there more to say about it? I'm sure there is. Certainly we could talk more about the maximum modulus theorem and things like that. What's that? No, we did not. There's these Pompeii's formula. Like there's a whole bunch of calculations you could probably do for like the anti-holomorphic functions. But anyway, we are now going to begin talking about integration. In the complex plane. And so I'm going to get straight to it. I start my chapter starts with this quote from Gauss in 1811, where it shows even then he understood all of the intricacies of it. But this stuff kind of came into its own somewhere in the 19th century. But here it is. Oops, definition. So integration of a complex function is done along a path. So we're going to let gamma from a to b, so ab is a real interval, be a smooth path. All right, and f of z, complex valued function Did I ever set the zoom? I was talking to you guys. I don't know if I remember ever setting the focal length on my camera. If I don't do this, it'll be fuzzy the whole time. There we go. Okay, sorry about that. F of z, a complex valued function, which is continuous. On and near gamma. And of course, by near gamma, what do we really mean is gamma of AB, right? This is the actual set of points that the image, the path covers, right? Let Z naught, Z1, Zn be an element. Now I say trace of gamma, and this is an artifact of the book I was looking at when I wrote these notes. But what I mean by that is the image of the path. All right, that's actually the set of points. So this is a parameterization of some curve in the complex plane, right? And gamma of AB, it's the set of points which the parameterization actually covers. All right. Anyway, so we're taking this set of points in the image of the path, and suppose A is less than or equal to T naught, which is less than T1, and so forth and so on until we get to Tn, which could be B, but it could be less than B. And we're supposing that gamma of Tj is equal to Zj for all j. All right. And all that's the setup. We define the integral along gamma f of z dz equal to the limit as n goes to infinity of the sum I equals 1 to n of f of zj times zj minus zj minus 1. Right? Now, that is one definition you could make, all right? I will prove that this definition is in fact equivalent to just writing the following. You could also say it's equal to the integral from a to b of f of gamma of t times d gamma dt, right? And, or if you like it in terms of real integrals, you could write it like this. It's actually equal to the integral over gamma of ux, oh my bad, u dx minus v dy, I'll put some parentheses on that, plus I times the integral, excuse me, of u dy plus v dx. And over here, we're assuming that f is, as usual, equal to u plus iv, right? Now, both this and this, without the I, right? These are both from Math 231. These are line integrals of vector fields in the plane. All right? So like, specifically, what I actually mean by that, technically speaking, is that the like the integral for, I'll just do one of them, but like the integral of u dx minus v dy over the curve gamma is actually by definition the integral from a to b of the vector field, let's say u comma minus v. Let me not say a to b. Let me in between step here. Integral over gamma of this vector field dot dr, right? And how we did that, we integrated from a to b. We took our vector field, we evaluated it at gamma of t, right? And then we took the dot product with what? The velocity. And then we integrated over time. Like that is explicitly the Math 231 Calc 3 definition of line integral as it applies to that particular vector field u comma minus v. So what I'm telling you is that the complex integral is really a pair of line integrals for two vector fields. Like you can think of the complex integral, it's a complex linear combination of the work done by u comma minus v plus I times the work done by v comma u. So it's the integral over gamma of, you know, u comma minus v dot dr plus I times the integral of v comma u dot dr. Now, I haven't proved this yet. I'm just making some assertions, right? I'm making some everything that's past the black is a claim. So let me show you why it's true. It's not particularly difficult, but it does require us to remember, like the, you know, the Riemann integral, that business. So let's get into it. All right. So let's see here. So the first thing we should notice is that if we look at zj minus zj minus 1 is equal to gamma of time j minus gamma of time j minus 1, we could take that and we can divide this by tj minus tj minus 1, and we can multiply it by tj minus tjy. Why can I do that? What have I assumed about these times? I've assumed they're distinct, right? So we're not dividing by 0 there. And then we can apply the mean value theorem, right? The mean value theorem, and select, let's say tj star, which is in the closed interval from, say, tj minus 1 to tj, right? For which what? Gamma prime of tj star is equal to gamma of tj minus gamma of tj minus 1. This is this is actually a bit of a cheat right here, but I'm not going to explain why. As I said, this will be justified in homework. So I'm telling you right now, I'm cheating a bit. I can't quite do this because the mean value theorem applies to real functions of a real variable. But this is a complex function, like gamma of t is complex. So I should technically apply the mean value theorem separately to the real and to the imaginary parts of gamma. And there's no reason that the same t sub j star should hold for both. However, in the limit we're taking, this difference is immaterial. So this lie does not hurt us, even though it's not technically true that there has to exist this gamma t sub t j star like that. I might have to pick a different t sub j star for the real part and the imaginary part in order to achieve this, instantaneous. Like what I'm trying to say is, like, I could say this. I could say, like, the real part of gamma prime at t sub j star star plus I times the imaginary part of gamma prime of t sub j star star star. Okay? Like, it doesn't have to be the same time, which gives you this average rate in principle, because the real and imaginary parts of the complex velocity here are not necessarily related. Anyway, moving on here. Let delta tj equal to tj minus tj minus 1. And we obtain the integral over gamma of f of z dz equal to the limit as n goes to infinity, right, of the sum, excuse me, j equals 1 to n, of f of gamma of tj times d gamma dt of tj star delta tj. What it is. You look,
Yeah.
Is there a particular thing here that's vexing? So then, this is, this is exactly the integral from a to b of f of gamma of t d gamma dt dt. Because I'm taking, the Riemann. So I'm extending the Riemann sum here to complex values, admittedly. If you want me to be a little bit more like directly using Riemann sums, what should we do? If we want to directly use real Riemann sums, I should do what? Right. So if I was to do that, this would be the limit as, n goes to infinity of the sum j equals 1 to n. I'm going to drop the, so we'd have like u, well, fine. So we'll say that d gamma dt is dx dt plus I dy dt. And so that would give us, u times dx dt minus v times dy dt times delta t plus I times the limit as n goes to infinity of the sum of j equals 1 to n of v dy dt plus u dx dt delta t. And now those are literally Riemann sums. Okay, because I couldn't fit it in, guys, but understand that the u and the v, so here I'm letting f equals to u plus iv as usual, right? And to be fussy, these are evaluated at gamma of tj star, right? To be more fussy, this should be evaluated at tj star star, and this should be evaluated at tj star star star. But in the limit, as n goes to infinity, these tj star star, they all end up going to the same. They're all pinching to the same thing.
And what's star star?
It's whatever it takes for the mean value theorem to give you the real part of that quotient. So like gamma is a smooth path, so gamma prime is differentiable. Like the real part of gamma prime is real differentiable, which means that I can look at the real part of that. That's a, the real part of this is the real part of gamma divided by the delta t. There has to be a particular time where the instantaneous rate of change of that is matching the average rate of change in the sense of the real part of the average. And the imaginary part has to be able to be matched by something else. So anyway, without me getting further into the weeds here, without having the notation to like fully, we could expand this into a page, all right? But the bottom line is, I hope I've shown you enough that you can see that what we're getting is just regular old garden variety Riemann sums, right? This is the Riemann sum. And that's the Riemann sum of what? Of the integral from a to b of, u of gamma of t dx dt minus v of gamma of t dy dt. I don't know why I'm I find myself writing the dependence again, but I'm not going to write it over here because I don't have enough room. A to b of v dy dt plus u dx dt. Which is what I was asserting over there, right? That this complex integral is actually two real line integrals added together. But let me just kind of like point out to you what all this means if we just, as is often the case in complex analysis, if we just follow the notation where it leads us, it's kind of the most dumb and obvious thing possible. What could it possibly mean, right? Like, check this out. All I'm really saying, so let's just look at this formal calculus. And the formal calculus will rediscover what we just derived by Riemann sums and all that junk. If I look at the integral over gamma of f of z dz, right? And I say, well, really I'm looking at the integral of u plus iv, right? And I'm looking at the differential of, I don't know, x plus iy, right? Because that's what z is. Z is x plus iy, right? So this is the integral of u plus iv times dx plus I dy. And see, if I was not teaching this class to math majors at all, if I was just teaching this to engineers who the proof didn't really matter, I would just do it like this. And I would say with authority, see, this is equal to this is equal to this, therefore, this is the integral of u dx. I times I is minus 1, so minus v dy, right? Pull the I out, and you've got u dy plus v dx. However you want to write those terms. I don't know, like, traditionally people don't put parentheses around these. I want to put parentheses. I'm resisting the urge at the moment. All right. There it is. That is the complex integral. And so you already know how to calculate line integrals from calculus 3. So hooray. You will remember how you previously knew how to calculate line integrals in calculus 3. Something, yes, from before the, yeah. All right, so, but the cool thing is we don't have to do that either, right? We can calculate complex integrals in a directly complex notation as well. So like, for example, unit circle, right? We have z equals to e to the I t, 0 less than or equal to t less than or equal to 2 pi, right? So dz dt is I e to the it, right? So with that in hand, you can integrate whatever functions you like around the unit circle in the complex, you know? It's like, what do you guys want to try to integrate around the unit circle in the complex? What function you want to take out for a spin here? What do you think?
How about cosh?
Gosh? Oh, man. Oof. Dang. Wow. Gosh. Ouch. I don't know. Now I'm scared. I'm scared. So I'll call the unit circle C. We're going to try cosh. I don't know. Like, I don't know about this one. The answer is 0. But I really don't want to calculate that directly. We're gonna put this away for later, okay? That was I welcome the interaction, but I'm going to trade you cosh for a reciprocal function. Because this one's kind of interesting, because it's not 0. So if we integrate that over the unit circle, we've got the integral like from 0 to 2 pi, right? And so notice what this really says. It says that dz is I e to the it dt. See that? So we can literally think of like plugging in the dz into here. Just like in Calc 3, we could calculate dx, we could calculate dy and plug them in and do the line integrals. That same kind of calculus, differential calculus, works here. Of course, you could also do this the logically straightforward way. I'll put it over here. Right, integral of dz over z is what? It's the integral of 1 over e to the it times dz dt, which is I e to the it dt, right? That's dz dt. Excuse me. This right here is the d gamma dt, right? And then dt. So I can look at it like that. This is my f of gamma of t, right? So I can do f of gamma of t times d gamma dt integrate over t. Or I can literally solve the dz dt for dz and plug it in. All paths lead to the same ultimate integral, which is that the e to the it's, they be canceling, and you've just got I times the integral from 0 to 2 pi dt, which is what? 2 pi I. All right? Gosh. Man. That's a savage request. I like it. Well, it's just a mess. It's just a mess. it's not hard to parameterize. It's just like that would loop me into integrating, you know, the integral of, see, when I plug in z for cosh z, I'd have e to the I gamma. So I'd end up integrating in e to the I times e to the I to the t. And after all that, it just integrates to 0. But I'm not sure that I could hack the direct calculus there. I know it integrates to 0 because I know a theorem that we should prove today. But before we prove that theorem, we should do some more elementary calculations like we did over there. Let's do a kind of a big one. Let us integrate. This will be useful to us. This might be a homework problem, which is music to your ears, right? I haven't looked at your homework, so, you know, odds of me doing your homework, they're high. You know? So, how about, so example 2. Let's look at the circle. Easy, turn off the camera. You're a monster. All right, see here. So let's put the center of this at z0. Let's let it have radius r. All right. So you guys tell me what is, and I've been using gamma for the sake of making a logical distinction in the definitions, but in practice we usually just put gamma equals to z for examples. So I'm going to write z equals to the parameterization around this circle. What would the formula be? To get to the middle of the circle, I put z0, right? And then I do r, e to the I. Instead of t, I'm going to use theta. All right, I'm going to let theta be my parameter. So theta is the t here. 0 less than or equal to theta less than or equal to 2 pi, because I just want to wrap around the circle once, all right? So this is the curve I'm interested in. Now what I want to do, I'm going to call that CR, because it's a circle of radius r, yeah? Then I'm going to calculate the integral over this circle of radius r of, let us say, z minus z0 to the power m dz. And I do mean that m could be an integer. It could be positive, it could be negative, but I do mean a counting number. If you count backwards, -1, -2, -3. What, I'm not allowed to count backwards? Those count numbers too. You don't count backwards? No? Oh.
No, integers less than 1 don't exist.
Well, you don't count then. Let's see here. Sorry. So what is dz? So here, my dz is just I r e to the I theta d theta, right? If you like, you could say dz d theta is I r e to the I theta, and then I multiply by d theta, if that makes you happy. But because that's how this actually goes. I mean, this is the integral from 0 to 2 pi of r, oops, my bad, z0, golly, z0 plus r e to the I theta minus z0, right, to the m as in mummy, power times I r e to the I theta d theta. That's my dz. Are we in agreement? I hope so. It went in. And it startled Violet. So I feel like that's a twofer. So Daniel will be proud of me. Let's see here. So Violet's like, don't bring Daniel into this. He hasn't earned it. So this is r to the, oh, I don't know, m plus 1? integral from 0 to 2 pi. Looks like we've got a e to the I theta to the m power times e to the I theta. Let me pull the I out. D theta. Pull the I out. That sounds kind of violent. So what is that? We have r I times r to the m plus 1 power, integral from 0 to 2 pi. And it looks like we're going to have e to the m plus 1 times theta all times I. Now I know how to integrate an exponential, right? So I just IR into the m plus 1 divided by I times m plus 1, e to the I m plus 1 theta, evaluate that thing from 0 to 2 pi. I don't know if I have put everything. My notes sometimes are in slightly more logical order than me here, in the sense that I sometimes put the cart before the horse. But in the proper sequencing of my notes, we should point out that, if you have an integral of a complex valued function of a real variable, so in other words, if I have, sidebar here, if I have the integral from, say, a to b of, suppose my g is a mapping from, say, ab to the complexes, right? So this is not a complex function of a complex variable. This is a complex valued function of a real variable, right? If I have that, I can rewrite that, in fact, as integral from a to b of the real part of g plus I times the integral from a to b of the imaginary part of g of t dt. All right, so that's the calculus which is at play here in this calculation. All right, and it's just so happens that if I have the integral of e to the, you can work it out, e to the, a times t, where a is complex, dt, well, it is equal to 1 over a e to the at plus a complex constant. That makes sense in terms of if you work out the real and imaginary part of this, because we already know that the derivative of the complex exponential works like it should. Anyway, what I'm trying to tell you is this calculus is actually meaningful that I'm writing. I'm not just making stuff up. Although I may not have given you all the definitions necessary to properly understand this calculation, my bad. But anyway, what is this? What's e to the 2 pi I? I mean, e to the I times m plus 1 times 2 pi. 1, right? So this is, the i's, they be canceling. R to the m plus 1 over m plus 1 times what? Times e to the, well, you just told me, Shane, that 2 pi times m plus 1 times I, and we've got minus e to the 0, but this is just a fancy way of writing 1 minus 1, right? So this is a big fat 0. Now why is that a lie? I mean, it's a partial truth. It is, in fact, usually correct. But there is one case where this calculation is pure nonsense. This assumes what? M is not 0. M could be 0. That's fine. M is not minus 1. Right. M equals to 0. M equals to 0 becomes this, actually. It's the integral of dz over CR, right? And so intuitively speaking, you're adding up the changes of z all the way around the circle. So what's the net change around the circle of z? It's 0, yeah. Yeah, that's 0. So that's not surprising. What is perhaps a little bit surprising is that in the case m equals 1, minus 1, there's something different happens here, right? This calculation's good for m not equal to minus 1. For m equal to minus 1, we have to go a different path. So this would be the, I times What happens when m is equal to minus 1? Let me do it in this color. So I get this I. M equals minus 1 means this is r to the 0, which is 1. So this front term goes away. And we've got the integral 0 to 2 pi. Right? M minus 1 is 0, so this is just 1. And lo and behold, 2 pi I. Just like example 1. Example 1 is that calculation with z not equal to 0. This is example 1 in the m equals minus 1 case with z not equal to 0. So generally speaking, don't put a 0 here. Put a 2 pi I, and then one of my favorite things, the Kronecker delta, m comma minus 1. In other words, this is 0, except in the one particular case that this is the reciprocal function. I would say that this single calculation already unveils the central mystery of the rest of this course, which is that the complex integral is sometimes non-zero, but in a kind of surprising way. See, because if you just look at these, like what's the difference? You got dz over z minus z naught, right? Versus the integral of dz over z minus z naught squared, right? Etc. It's easy to understand that there's something funny that goes on with this integral at the origin. I mean at z naught, right? Because at z naught we got what? We have division by 0, right? So you can understand that that is apparently where that 2 pi I is coming from. But then you're left with the quandary, why doesn't it keep happening for higher powers? Aren't higher powers worse? Why don't those give you? Why don't those give you 2 pi I or something worse? But they don't. It's just the reciprocal power that gives you a non-trivial integral in this sense. Why is that? That is the mystery which we will solve in the remainder of the semester. So you got that one. Another example. There's more to life than circles, so let's do a line segment, right? How do you parameterize a line segment? You're like, oh, I know, I remember from Calc 3, right? No? Why do I even have a prerequisite of Calc 3 for this course? I don't even know.
MT plus B, right?
MT plus, oh yeah, I guess I should, fair enough. Let's go from point P over here to point Q, you guys. Z equals to what? We'll parameterize that. Golly. Ah. I tell you what, it's annoying. How do you parameterize that? What did you tell me?
I said MT plus B.
Wait, what? NP?
MT.
Oh, MT. Oh, no. You hurt me with that. How dare you? So P, you're joking. P plus T times, very nice, Q minus P, right? So this is the parameterization of the line. Because remember how this works? This is for 0 less than or equal to T, MZ plus B. I kill you. So I ever tell you guys there's a professor at NC State who used to like teach like business calc, and he'd tell the students like, I come into the hall after you're done with my class, I come up to you, I say, what's the fundamental theorem of calculus? And you go, I don't know. I kill you. This guy, his name was Moody Chu. He was taking selfies of himself like years before anybody else was. He just had like a digital camera. It's just like holding it like this. Like this is like 10 years before selfies were a thing. That was his picture on the, anyway. So that guy was funny. So this is a parameterization of a line segment. Going from when I put z equal to 1, when I put t equal to 0 rather, I get p. When I put t equal to 1, I get p plus q minus p, also known as q. So this is the standard trick to parameterize a line segment going from 2 points. So with that in mind, we can calculate an integral of, let's see here. What do I do next? Integral of z to the n dz along, let me call this line segment L for lack of imagination. L. So that is, wowzers, the integral from 0 to 1 of parentheses p plus t times q minus p to the power n times the derivative of, what's the derivative of z with respect to time? It's just q minus p, right? dt. And I guess the thing I keep using in these, I just can't read my own notes. I have made the comment before these notes that the FTC naturally extends. Like it is true here, guys, that the integral, if you have like df dt is equal to like df1 dt plus I df2 dt, so like this, is equal to f. In other words, this is a map from the reals to the complexes, all right? So a complex valued function of a real variable, we can extend the notion of anti-differentiation like this. So like, for example, then if you have the integral of f dt from a to b, it is still the case that that's equal to f of b minus f of a, right? Where here, like I'm saying f is like f1 plus I f2, something like that. The point is, you have the integral from a to b of f1 dt plus I times the integral from a to b of f2 dt. So you just apply the regular fundamental theorem of calculus part 2 separately to the real and to the imaginary parts. So you can still do the calculus just like that. And so what I'm telling you here is, even though this is a complex quantity, we know how the calculus works out here, right? So like this is still sorry guys, 1 over n plus 1, right? Times p plus t times q minus p to the n plus 1. And this is still riding along, I suppose. Well, actually, do I just need this? Well, you guys tell me. If you differentiate this, do I get back to the integrand? That's really my question.
Don't you need to divide by 2 times p as well?
Do I, though? Because if I differentiate this, right? This is the form u to the n plus 1 divided by n plus 1, right? And if I differentiate that with respect to time, I get, u to the n times du dt. That's the chain rule here, which we proved. But du dt is this right here. See?
Oh, you're not evaluating, are you?
This is that. So. And then, of course, yeah, I'm not done yet, but yeah, the FTC 2 says that I have to evaluate from 0 to 1. Like so, right? This is a side comment. And so what do you get? You get, putting in 1, I get q, so I get q to the n plus 1 over n plus 1 minus p to the n plus 1 over n plus 1. All right. So we can keep doing calculations directly from the definition like this if we like, you know. In fact, my next example in the notes, I do a similar, like the example 7.1.5 in the notes, I look at the integral of, I won't go through the details in this one, but like the next example are on here. This was 4? Oh, okay. So example 4, I think I do integral over the line of like z to the power c dz, where c is a complex power, and I say c not equal. Now, to be clear, what was the, now there's something that was, there's some fine print here I left out, which is kind of important, which is what? N not equal to what? -1, right? That special case, just like in Calc 1 in the real case, 1 over x is a special thing, right? 1 over z is a special thing. And again here, is z not equal to -1, right? But you can work through that. Well, essentially by one of the problems that you had on the test, you can still essentially work out that this is going to be like z to the c plus 1 over c plus 1. And you evaluate from p to q. So it's just the same thing again. But now, of course, I'm talking about the complex power function, you know, as we define in terms of exponentials and logs and all that jazz. So I don't, well, I'm a little bit apprehensive about this example. I got to think about something here for a second. Let's see here. Well, okay, so the fine print here is I have P and Q fall in a subset of C on which a single value of Z sub C is defined. So we are assuming that that like this is Z, you know, ZC is the exponential of C log alpha of Z, let's say. And that, you know, okay, so there's, as you guys know, there's this branch somewhere we're missing, right? At angle alpha. And for this example 4 to make sense, it must be the case that P and Q are something like this, you know? They can't, the line segment at least, if I don't want the line segment to cross the branch cut. If I did that, then I would need further analysis, okay? And we'll talk about that as time goes on here. How you deal with that kind of thing. All right, so this is, up to now we've just looked at curves that are parameterized by a single, you know, a single path, right? But not every path can have a single parameterization, right? So I defined the complex integral for a smooth path, but there's a natural extension to piecewise smooth paths. How would you think we'd do that? So sometimes a piecewise smooth path is called an arc in complex analysis. Sometimes it might be called a contour. Sometimes this integral we're talking about is called the contour integral. But a piecewise smooth path, so a definition, if C is equal to like C1 union C2 union Cn, where C sub j is smooth with parameterization gamma, let's say sub j, a mapping from, for lack of imagination, a sub j comma b sub j to the complex plane, these are smooth, such that, you know, gamma sub j of b sub j is equal to gamma sub j plus 1 of what? What should I put there?
Oh, AJ.
AJ, very good. AJ. So what I'm saying is that the parts of the path link up, right? I guess that's a j plus 1, right? So like this point right here is gamma 1 of A1. This is gamma 1 of B1, which is equal to gamma 2 of A2. That point right there, right? This point right here, if you understand my language here, this is gamma 2 of B2, which is gamma 3 of A3, et cetera, right? Right. Now, you don't have to use this setup exactly like I did, but this is the basic idea. Is if we were to define the integral of f of z dz over such a curve, it's simply defined to be well, I mean, we could define it this way. It's really just the sum I equals 1 to n of the integral over the j equals 1 to n of cj f of z dz, right? So we just simply add the integral on each sub piece like that, which if you want me to get into the minutia of it here, it's the sum j equals 1 to n of, you know, integral from a to j to b to j of f of gamma sub j of t times d gamma j dt dt. We could have taken that to be the definition, by the way, of the complex integral if you wanted. Like I gave a more Riemann style definition, in part because it makes one proof in my notes easier. But I think I have the other proof in your homework, so hooray. I do want to get to the theorem that I mentioned. Let's see if I got time. We got time. All right. I'm going to use the projector here. Or not. Let's see here. I guess I keep writing. You guys like it if I write, don't you? Yes? No? Maybe so? Yeah, all right. Yes, please. I think this example I'm erasing at the moment, I have in a slightly different order in the notes, but anyway. So just to give you an example where we need different parameterizations for different pieces, one of my favorite examples is like the integral over a half circle. So we'll do the integral of z squared over the upper half circle. Integral over, let's see, what did I call it? C, well I called it C. Z squared dz. And so the circle I have in mind is just this. It goes, let's see here. Make sure I got the orientation matters, right? Line integrals are oriented integrals, and so are the complex integrals. So we're going to say the counterclockwise oriented of the upper half disk. So it goes this way and that way. All right. So I'm going to call the upper half circle here CR plus. And this guy down here, we already have a notation for. It's minus R to R, right? Talked about that before. So this is the integral. We can say integral from minus R to R of z squared dz plus the integral over CR plus of z squared dz. So, all right. So what we're up against here is the integral from minus r to r of x squared dx plus the integral from 0 to pi of r e to the I theta quantity squared times r I e to the I theta d theta. Let me expand on what I'm saying. Why am I saying that? Because this right here, right, is z equals to x for minus r less than or equal to x less than or equal to r, right? That is the parameterization of a z here. And dz is dx. So that's why we have x squared dx here. Okay? And the upper part, right up here, I have z equals to r e to the I theta. That's a parameterization of the half circle, and I go 0 to pi. So I get myself, you know, x cubed over 3 evaluated from minus r to r. And over here, what do I got? I've got a r cubed, it looks like, right? Integral from 0 to pi of what? E to the 3I theta? D theta? De Moivre's theorem gives me 2I theta plus I theta is 3I theta. There's an I, I'll pull it out. Great, so we get r cubed over 3 plus r cubed over 3, I guess. And then plus what? Oopsie. Be careful here. Do I get a plus there? Whoa.
The whole thing on the right would be negative.
The whole thing what?
The whole thing on the right, well, no, because 3i sine theta is...
Oh.
3i theta would go to negative 1.
Yeah, IR cubed, and then we've got e to the 3I pi over 3I minus e to the 0 over 3I, right? Oh, the i's cancel, don't they? And, okay, I think my notes are wrong. But I knew that the answer in the notes is not wrong for reasons I'm about to share with you. So look, it's like I knew that the answer to this is 0, guys. I knew that. So my notes are a little bit sketch. Or maybe, oh, I'm just reading them in the wrong order is all. It's fine. The notes are fine. Never mind me. So it does work out to 0. All right. Move on here. I'd really like to explain to you why why I know it's 0. Let's see here. But we have a little bit more background to go here. Actually, I'm going to use the projector for this little bit here. No, I won't, because then you guys don't like it. Sorry. I'll make up my mind eventually, guys. Definitely.